Next, let us look at another property. Supposing I is a finite interval such that I is contained in union 1 to n i's, where a finite union of the intervals, but we are not longer saying that they are disjoint. Then the claim is that length of I must be less than or equal to summation length of these intervals a i's. So, if we drop the condition that these are pairwise disjoint, I is a subset of. So, we are saying if an interval I is covered by a finite union of intervals, then the length of I must be equal less than or equal to summation of length of these intervals i's. Let us look at a proof of this. The proof of this is once again similar to the earlier property. So, let us say we are saying I is contained in union of i's, I equal to 1 to n. Obviously, if one of I is infinite, then clearly this implies length of I is less than or equal to summation length of i's. That is obvious, because one of these terms on the right hand side in the summation is plus infinity, which is always greater than or equal to length of I, whatever be I. So, let us suppose that each I is finite, and this is a finite union. So, that implies I is finite. So, without, as before, without loss of generality, assume without any loss of generality that I is equal to a comma b. So, here is once again the same picture, here is a and here is b. Now, the point A belongs to the interval I. So, this is my interval I. So, A belongs to I, that means it belongs to this union. So, it will belong to at least one of the intervals i's. Let us name any one of them which contains the point A to be I 1, and let us say the end points of that is A 1 B 1. So, the point A belongs to one of the intervals i's because it is in the union. So, it will belong to one of them, say I 1, and let us say the end points of I 1 are A 1 B 1. So, here is the end point A 1, here is the end point B 1. Now, the possibility is this B 1 is on the right side of B, right. So, one possibility is it is on the right side of B. So, either, so let us just write either B 1 is bigger than or equal to B. That means, my picture looks like here is A 1, here is A, here is B and here is B 1. Then length of I, which is equal to B minus A, is less than or equal to B 1 minus A 1, which is equal to length of I 1, and which is obviously less than or equal to summation length of i's, I equal to 1 to n. So, in the case B 1 is on the right side, we are obviously through by this case. So, what is the other possibility? Case 2. So, suppose this is the picture. So, suppose this is the picture, namely we have got A, we have got B, and here is A 1 and B 1 is on the not on the right side, but on the left side of B. So, let us take that as the picture. So, in that case the point B 1 belongs to that union. So, B 1 is in the interval A B. So, it will belong to that union. So, it belongs. So, B 1 belongs to I. So, it belongs to union. So, it will belong to one of the intervals in the i's. So, let us call that as some interval I 2. So, B 1 belongs to I 2. So, that means A 2 must start here and B 2 either it will be somewhere here or it will be on the right side. So, and if it is on the right side of it, that means what? So, let us say it is on the right side. So, here is B 2 instead of here, let us say B 2 is here. Then the length of the interval I. So, length of the interval I, which is equal to B minus A, which is B minus A, is less than or equal to B 2 minus A 1, B 2 minus A 1, which is less than or equal to B 2 minus A 2 plus B 1 minus A 1. So, B 2 minus A 1 is less than or equal to B 2 minus A 2 plus B 1, we are adding something bigger, and then A 1. So, that is length of I. So, in that case length of I will be less than or equal to length of I 1 plus length of I 2, and so that is anyway less than or equal to summation length of i's I equal to 1 to n. So, if we go on repeating this process, so what does it mean? So, in the next stage, so what is the other possibility? That B 1 is inside. So, that means here is A, here is B. If it is not outside, that it must be inside. That means here is A 1, here was our B 1, here is A 2, and somewhere here is B 2. It is not on the right side, it is on the left side. So, once again B 2 belongs, and then we can proceed in the same way. So, either at some stage we will be through, or eventually if not, then we will have A 1 is less than equal to A, is less than or equal to A 2, less than or equal to B 1, less than or equal to B 2, less than or equal to so on, less than or equal to A n, less than or equal to B, less than or equal to B n. So, what we are saying is either we will be through at some finite stage, or we can rearrange eventually after n stages the end points in that way. In that case, again lambda of I, which is equal to B minus A. So, here is A, here is B, is less than or equal to same idea B n minus less than or equal to B n minus A 1. So, go on adding and subtracting less than or equal to B n minus A n plus B n minus 1 minus A n minus 1, and so on, and plus B 1 minus A 1, and that is equal to sigma lambda of I j, j equal to 1 to n. So, it is just whenever we are in a finite stage, the endpoints can be rearranged nicely, and we get the property, namely the length function is having the property whenever a interval I is covered by a finite union of intervals, then the length of I is less than or equal to summation length of I i's. Let us look at an extension of this property, namely supposing I is a finite interval such that I is covered by a union of intervals I i's 1 to infinity. That means, the interval I is covered by union of a countable union of intervals I i's. Then again the claim is length of I is less than or equal to summation length of I i's. So, let us prove this property, and keep in mind here we are assuming our interval I is a finite interval. So, interval I is contained in union of intervals I i's, I equal to 1 to infinity. These are intervals I finite. This implies length of I is less than or equal to summation length of I i's, I equal to 1 to infinity. This is what we want to prove. Obvious case, note, if any one of the terms on this side lambda of I is infinite, then we are through. So, that is, note, if I is infinite for some I, then what will happen? Length of I will be equal to plus infinity, which is bigger than or equal to length of I, whatever it may be, whether finite or infinite. So, that is, so implies sigma length of I j j equal to 1 to infinity is also bigger than or equal to lambda, because one of them is infinite. So, that case is obvious. So, let us assume not only I is finite, all the intervals i's are also finite, and we want to check this property. So, what we want to check is the following: I finite, say endpoints say a b. We can assume it is a closed interval, because the length of I is not going to change. Each I j is finite with left endpoint A j, right endpoint B j. We are not saying that we are assuming these I j's are open or closed or anything. We are just naming the endpoints, the left endpoint of I j. So, we are saying I looks like A and B, and each I j is A j B j. We are not saying that these endpoints are included, and we are given that I, which is A comma B, is contained in union of I j equal to 1 to infinity, right. And if this was finite, then we already know how to manipulate that we have already done earlier in the previous case. So, the idea is from that infinite union bring it to a finite union, and here is a closed bounded interval contained in a infinite union, and we want to say this is going to be contained in a finite union. So, somewhere the compactness property of the interval a to b is going to be used. So, but for that we need the intervals to be open. So, let us make these intervals I j is open, but of course, the lengths will change. So, let us fix, let epsilon greater than 0 be fixed, select an open interval, say call it as j j, such that this j j includes our interval I j and does not change the length much. So, length of I, length of this j j is equal to say length of I plus epsilon. So, slightly increase. So, what we are saying in this picture, take a interval from here to here, the open interval from here to here, call that as j of j. So, each I j which was from A j to here B j is enclosed in an open interval slightly bigger, but the length. So, this is the length portion that you add, that at the most is equal to epsilon. So, now what happens is the following. So, A b is contained in union of I j's, and each I j is contained in the union of j j's, and each j j is a open interval. So, we have taken a open interval. So, we have got a open cover of the closed bounded interval a b. So, implies by Heine-Borel property of the real line, which says whenever a closed bounded interval is covered by an collection of open intervals, then implies there exists some n such that finite number of them will cover it. So, A b will be contained in union of j equal to 1 to n j j's. Finite number of them will cover it. And now, implies by our earlier case that length of I. So, this was my interval I. So, length of I is less than or equal to sigma length of j j's 1 to n. Okay. Now, each one of them is less than or equal to sigma j equal to 1 to n length of I j plus epsilon. And now, we want to separate it out this summation and let it go to infinity and equal 1 to infinity. But the problem will come because of this summation epsilon added n times, that summation will tend to become very, very large. We do not want to happen that. So, what we go is we revise our construction. So, where we selected for a given epsilon fix, select an open interval j j such that this is so, instead of epsilon for the interval I j, let us divide it by 2 to the power j. So, instead of having this extra length to be equal to same length as epsilon for every interval I j, for I j we want this extra length to be equal to epsilon by 2 to the power j. So, once we do that, we are in a better shape, because now this estimate will be 2 to the power j. So, that means, it is less than or equal to summation j equal to, I can put it 1 to infinity, because it is less than or equal to lambda of I j plus summation epsilon by 2 to the power j, j equal to 1 to infinity. And now, this series is convergent, because it is a geometric series with common ratio 1 by 2, which is less than 1. So, this term is equal to epsilon. So, what we are saying is length of I is less than or equal to summation length of I j's plus a number epsilon, but epsilon was arbitrary. So, let epsilon go to 0. So, we will get length of I is less than or equal to summation length of I j's. So, what we are saying is that the countable property that we looked at, namely length of I is less than or equal to summation length of I i's, whenever a interval I which is finite is covered by any countable union, then the length of I is less than or equal to length of I i's. So, this is we have extended that earlier property from whenever a finite covering is there, we have extended it to a countable infinite covering, but only for finite intervals. But we would like to extend this to even arbitrary intervals which are not necessarily finite. So, for that we will have to do a little bit of more work. So, let us look at the next property, which says the following. Let I be a finite interval such that I is equal to union 1 to infinity I n, where I n's are pairwise disjoint, then at least we can conclude that the length of I is equal to summation length of I n's. So, whenever a finite interval is a countable union of pairwise disjoint intervals, then the length of I is equal to summation length of I n's. So, let us prove this property. So, what we have got, I is equal to union of I j's, j equal to 1 to infinity, I j's are pairwise disjoint, I finite implies length of I is equal to summation length of I j's. So, let us observe, note, we have already proved just now that if a interval is written as this, a union of countable disjoint union, note length of I we have just now shown is less than or equal to length of I j's added up, j equal to 1 to infinity, call it 1. So, length of I is less than or equal to, this is just now we proved for finite intervals. So, only to show that length of I is bigger than or equal to summation j equal to 1 to infinity length of I j. So, only this is to be shown, and for that, so here is the interval a to b. Okay. I is finite. So, here is the interval finite interval I. Now, look at I 1 is a subset of I. So, it should be somewhere inside. So, somewhere is A 1, somewhere is B 1. Similarly, I 2 is also inside I. So, somewhere it has to be, either it has to be A 2 here, B 2 here, or it could be here somewhere, right, and so on. So, for every n, let us consider the endpoints, A n, B n of I n's. Okay. We can arrange them, there are only finitely many of them, such that here is A, here is A 1, here is B 1, here is A 2, here is B 2, and so on, here is A n, and here is B n, and here is B. That means, we can arrange them in such a way that A is less than or equal to A 1, less than or equal to B 1, which is less than or equal to A 2, less than or equal to B 2, and so on, less than or equal to A n, less than or equal to B n, and which is less than or equal to B. Once that is done, so this implies by a simple algebra, that means length of I, which is equal to B minus A. Now, this is B, this is A. I am going to make it shorter B n and A 1. So, this is bigger than or equal to B n minus A 1. So, which is bigger than or equal to B n minus A n plus B n minus 1, the next one here, minus A n minus 1, and so on, plus B 1 minus A 1. So, this put together is nothing but which is equal to sigma I equal to 1 to n length of I I. So, what we are saying is, for every n, the endpoints of the intervals I 1 up to I n can be rearranged in this fashion, and hence by looking at the ordering of this, length of I is bigger than, and this happens for every n. So, that implies length of I is bigger than or equal to sigma I equal to 1 to infinity, because this is happening for every n, I can let it go to infinity length of I. So, the other way around inequality is also proved. So, that means, we have proved that whenever I is a finite interval, which is written as a countable union of pairwise disjoint intervals, then length of I is equal to sigma length of I n's. So, with that we prove an important property of the length function for finite intervals. We will continue our study of the length function in the next lecture. Thank you.